Alright, today in Concept App we're going to be continuing on talking about gases. We're going to be doing a specific type of calculation as well. So first off, let me just mention something that we briefly talked about earlier in the year about molar volume. Molar volume is the volume occupied by exactly 1 mole of a gas. You can determine this for a gas by dividing the GFM of the gas by its gas density. Now the molar volume of any gas at STP, so at 1 atm and 273 Kelvin, has a volume of 22.4 liters. So that's where that number comes from. We've talked about that before and using that when we did dimensional analysis. So again, this only works for a gas, that 22.4 liters, and again that's equal to 1 mole of it, as long as again they're at the same pressure and temperature. Now, that applies and comes along with Avogadro's law. Gases at the same temperature, pressure, and volume have to contain the same number of particles. So when we talk about temperature, pressure, volume, and number of particles, for any gas samples, if 3 of those 4 quantities are the same between them, then the 4th must be equal. So we'll do a bunch of practice problems with those in class. Here's a couple of little things we'll go over right now. With Avogadro's law, and we have these 3 samples, helium, nitrogen, and methane. Which one has the more gas particles? They're all the same amount. If we look at their volume, pressure, and temperature, they're all equal, so they have to have the same number of particles, which you can see on the bottom part of the picture. Now, which one will behave most ideally? This ties into our last concept. Even though we have the same number of particles and they're at the same temperature and pressure, that means then that we're solely looking at the effect of IMFs. So we're looking for the smallest gas particle, which would be helium. So helium, which has the smallest particle, would behave the most ideally out of all of those samples. So here's an example of a multiple choice question that I was mentioning. For example, which sample of gas below contains the same number of molecules as a 2-liter sample of oxygen at 300 Kelvin that's at 100 kilopascals? So the thing you want to focus on, it doesn't matter what the formula of the gas is, you're looking for them to have the same volume, temperature, and pressure. So based off of that, C is the correct answer. The 2 liters match, the 300 kelvins match, and the 100 kilopascals match. So the same pressure, temperature, and volume have to have the same number of molecules. Now, both Avogadro's law and the kinetic molecular theory can be used to explain the relationship between pressure, temperature, and volume of a gas. If we change pressure and temperature, what happens to volume? If we change pressure and volume, what happens to temperature? So we can analyze these 3 different variables under different conditions. Now, the combined gas law, this is used for gases only when all 3 variables, pressure, volume, temperature, are changing. This does not depend on the identity of the gas, so it doesn't matter what the formula of the gas is. We're just concerned with the pressure, volume, and temperature. So this formula, we're going to use it in its entirety when all 3 variables are changing. One big thing that students always forget is that temperature in this calculation must be in Kelvin. So if it's given to you in degrees Celsius, you must add 273 to the temperature before going ahead and solving the problem. Alright, so let's do some examples with this. So we have a 2-liter sample of gas at STP that is heated to 500 Kelvin and compressed to 200 kilopascals. What is the new volume of the gas? So first off, the thing I want you to keep in mind is when we're doing these calculations, if you see STP anywhere in the word problem, I want you to circle it or highlight it, underline it, because that's actually giving you data that we're going to input in. So here I have my combined gas law. I'm using all 3 variables because they're all going to be changing. And then I'm going to input my information given to me. Now, the 2 liters, I can clearly see my word problem. The 1 atm and 273 Kelvin comes from STP. So I'm plugging in my 1 atm and 273 because those are the standard temperatures and pressures. I'm plugging in my new temperature, 500, and then I decided to convert my kilopascals to 2 atm. Now, you can also do this in the opposite fashion. You could, instead of putting 1 atm, you could put 101.3 kilopascals. Either way, you're going to get to the same result. Here I just decided to make it in atm. So what is our new volume of the gas? We're going to basically be cross-multiplying here and then dividing each side by the product of 273 times 2. And when you go ahead and solve the math correctly, you get 1.8 liters. So when I increase the pressure and increase the temperature, my result is a slight decrease in volume. All right, another example. Similar types of values that we're working with. There's no STP here, so all the values that we can visibly see in our word problem we're going to be using. Again, we're using the full combined gas law example and plugging in our values. So I have a 1 atm pressure, a 2-liter sample that's at 300 Kelvin. I'm changing it to be at 500 Kelvin and 1 liter. So what is the new pressure? So again, by cross multiplying, dividing each side, I get a volume, or that should say, I'm sorry, pressure of 3.3 atm. So go ahead, I'm going to show you this right now so that there's no confusion. That should say 3.3 atm, and that is my new pressure. All right, so make sure you make that change as well if you accidentally started to write it down. So again, when we increase the temperature, decrease my volume here, I see then that I get a pretty big increase in pressure. All right, so we'll work with this formula for tomorrow in class, and our next concept is going to focus on when we're only using 2 of the variables. All right, you are all set.